Okay, good afternoon. Welcome to the lecture of elementary principles of the chemical processes. So, last week, right? Yeah, last week we moved to the topic of from the chapter 5 to the chapter 6, which is related to two phases. Especially we focus on the gas and liquid phases in the beginning. So, so there's a very important point to understand is that you need to first of all you need to know the how to know the diagram, phase diagrams according to one single species. Okay, this is this is a kind of phase diagram, right? And then after that, for the gas and liquid system, it's important to know vapor pressure. Okay, if you know the vapor pressure, you everything is related to vapor pressure, and vapor pressure is related to the volatility. If you have a high volatility for one species, that the vapor pressure will be higher. Okay, and then after that, we start to know how we start to need to know that how to estimate the vapor pressures. Okay, for the single component. This is single component. Okay, so we introduce you three equations. The first equation is called Krypton equation. Krypton equation is today you find out this is ladies and gentlemen, what is this? H. Can you tell me what is this in Chinese? 0.5 point. Can you tell me Krypton equation? This is a Krypton equation, right? You know this is pressure, right? This is temperature. This is volume. Okay, this is temperature. And what's this? Yes, 潜热, right? Okay, thank you, 0.5. Does anybody want to tell me the physical definition or physical meaning of the latent heat? Latent heat is 潜热. Anybody want to tell me? A little bit details. What is latent heat? What is 潜热? Yes. Okay, thank you very much. Very good. The gentleman over there tells us that that's the energy gain or lose when you change the phase. Okay, change the phase from liquid to solid, change the phase from the liquid to gas, and the energy required for changing the phases is called latent heat. Okay, okay, good. Thank you. Very good. I'm very happy. So this is first equation. The second equation is so first equation is to let us realize or let us find out latent heat. This is called Krypton equation. The second equation is Clausius-Krypton equation. And once we know the latent heat, this is the second equation. Once we know the latent heat and what we need to find out relationship between pressure and temperature, what we need to know is how to find out B first. B is a constant, a coefficient, a constant. So you need to have two, as you know that, this is, if you plot a relationship between pressure and temperature, you can have, for example, the y-axis is pressure, x-axis is a reciprocal of temperature. So you can plot a straight line, right? You can plot a straight line. Okay, and then once you have a straight line, this is the reciprocal or intercept. This is intercept. Okay, so in order to realize constant B, you need to have at least 2 points, which is related to the pressure and temperature. And once you have these 2 points, you can find out the constant B. And once you find out constant B, you can get the third. You can have that relationship. You can have this equation. So no matter what, I give you a temperature, you can find out the pressure. Okay, this is what? This is the vapor pressure. Okay, this is the second equation, Clausius-Krypton equation. And Anthony equation is a kind of empirical equation. What is empirical? What is empirical equation? Does anybody want to tell me the definition of empirical definition? 0.5 point. What is empirical equation? You know, you have constant A, B, and C. What's empirical? What's empirical? Meaning of empirical? If you tell me and you got the answer right, I will be very, very happy because I think, wow, you are qualified to pass this to pass this class, right? Yes. 经验得出来的 Thank you. 0.5, very good. But empirical equation is very different from theoretical equation. Theoretical equation, for example, E equal to mc squared. That's kind of theoretical equation. That's not experiment. You don't do experiment and you find out this equation. You got this equation because you do a lot of calculation, mathematical equations, and you realize E equal to mc squared. But empirical equation means that you do a lot of experiment and you don't know why. And you fit A, B, C as a constant. So you got a relationship between the pressure and the temperature. This is what we call is empirical equation. Okay? So Anton equation is a kind of empirical equation. There are many, many experimental data in order to get this equation. And there's no physical meaning of A, B, and C. So you just know this is a constant. Okay, so if you have a table A, B, C for water, for ethanol, for whatever, for carbon dioxide, benzene, then you realize the relationship between pressure and the temperature. Okay, and finally is kind of we call Koch chart. The Koch chart again is a kind of chart, and you use the chart to realize the relationship between pressure and the temperature. That's it. Okay, in the end of the lecture last week, we talked about Gibbs phase rules. Gibbs phase rule is that if you want to duplicate some of the environment between gas and liquid, and you need to know how many information you need in order to duplicate this system. And what we need is that we call degree of freedom. If degree of freedom is equal to 0, that means the condition is fixed. Everything is fixed. For example, this point, A point, everything is fixed. Temperature fixed, pressure fixed. So you can get this triple point, right? But if the temperature and pressure is not fixed, you can move this point around in this phase diagram. You can put this point here, 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 whatever. Okay? So Gibbs phase rule, the meaning of Gibbs phase rule is to tell us that how many information needed in order to duplicate or in order to create a system which you want. Okay, so df2 is a number. What is C? Does anybody want to tell me what's the physical meaning of C? Raise your hand. 0.5. Yes. 物质. Not exactly, but anyway, I can give you a point. No problem. Okay. So C means how many species in this system? In this system, how many species in this system? Okay. What is pi? Pi, yes. Okay. Thank you. Thank you. Very good. 0.5 point. The phases. How many phases in this system? If I have solid, liquid, and gas, how many systems in this system? 3, right? Because liquid, solid, and gas. So you can put 3 in this place. Okay, so according to this equation, you can realize how many information are needed in order to create a system. Okay, good. I think I already give you a lot of points. Hope you are happy with this. Right, okay, so today we move to the section 6.3, which is one condensable component. Gas liquid system, we only dealing with one condensable components. So I just want to recall what we have learned last week. That is that if you have many gases, many type of gases in a gas phase, for example, you have nitrogen, argon, oxygen, carbon dioxide, and only one condensable species, which is water. And this is the topic we are going to talk in section 6.3. Okay, so I think I have talked about this with you. That means that only one condensable components in this system, which is A, for example, and A we can regard this as a water. So the molar fraction in the liquid phase is only 1. So the XA, the molar fraction of the water is always 1. There's no other species like carbon dioxide, oxygen. No, because we're only dealing with one condensable component. For example, if we have two condensable components like water and alcohol, okay, ethanol, that this is not the case we are going to talk in section 6.3. And that will be the case we are going to talk in section 6.4, the next topic. Okay, but of course, we always start from the very simple case first, and we move to the complicated cases later. Okay, so today we start to talk about this easy case first. So because you need to use a little bit imagination to think of this. So what I want, let's repeat this topic one more time. Imagine you have a dry air. There's no water in this system here. And the temperature is 75 Celsius. The pressure is 760 millimeter mercury, which is 1 atm, right? Okay, at this time, you pour the water, so the vapor pressure of water is 0 because there's no water. There's no water. Okay? And then you start to pour the water into this system. What happened? You have water, of course. And then you will have what? You will have vapor because the water 75 Celsius, the water vapor will be, you will have a lot of water vapor in the gas phase. So the vapor pressure of water will be larger than 0. That's for sure, right? That's for sure. Okay. And then eventually, when you wait for a period of time, when you wait, and the water eventually the rate of the evaporation will decrease, and eventually there's no vapor. Eventually, the rate of the vaporization and the rate of the condensation of the water will be equal. So vaporization speed and the condensation speed will be equal. And at this time we call saturation, or we call it equilibrium. So the vapor in the gas phase of the water is saturated. We call it saturation. Okay, let me say it again. The vapor of the water is saturated in the gas phase. Okay, so what does that mean? So this means two phases reach equilibrium. Okay, no change occur in the amount of the composition of either phase. Somebody read either. This is English accent and American accent. Okay, it doesn't matter. Either. Okay, either phase, equilibrium. Okay, and then the gas phase is then said to be saturated with water. Okay, and this is what we call saturated vapor. Okay, so you understand this? No problem. So at that time, you can change the temperature and pressure, right? Because if you change the temperature and pressure, you will have different vapor pressure. Or I should say you will have different saturated vapor. Okay, you will have different vapor pressure of the H2O. Okay, so we can play temperature and pressure to get different value of the vapor pressure. Okay. However, because this is only one condensable component in this system, so the fraction of the fraction in the liquid phase of the water is always equal to 1. Okay, please remember this. And then if we tune a different temperature and pressure, we will have different what? Vapor pressure, right? But what we care in this system is that what's the molar fraction of the water or molar fraction of the vapor. Okay? So how can we get this? So there are two important things is that we know the total pressure because we know that's what we tune, right? That's why we can change the different pressure in the gas phase. Okay? And then we need to know what? We need to know the partial pressure of the water is equal to molar fraction times the total pressure. Why is this called? Dalton's law. You learned this in chapter 5. I hope you remember this, chapter 5. Okay? So, let's take a look of the DOF. So there are three variables. So if we go back to this system, and remember this system is already reached to the saturation. It's already reached equilibrium, and this is called saturated vapor. Okay? So if you change the different, there are three parameters. If you change the pressure and temperature, you will get different molar fraction. Okay, so there are three variables now. So if we think of DOF, do I need to tell you these three in order to create this system? Or do I need to, how many information I need to give you in order to create this system? 3, 2, or 1? If I tell you the pressure, can you create this system and then the number of the temperature and the molar fraction of water will come out? Let's find out because use DOF, right? So 2 plus C minus 1, how many species in this system? 1. A, 1. B, 2. C, 3. D, 4. Which one? 2, right? 2, right? Why? Air and water. You might say, Professor, no. 3. Why 3? Because oxygen, nitrogen, and water, right? No, because we are talking about independent variables. Remember, we talk about independent and dependent equation, dependent and independent variables, dependent and independent blah, 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 blah. Okay, because the ratio of the oxygen and nitrogen is fixed. So once you know the ratio of the oxygen, you will automatically know the ratio of the what? Once you know the fraction of the oxygen, you'll realize the fraction of the nitrogen. So oxygen and nitrogen is not independent, it's dependent. So you only have one variable. So here is 2. How many phases in this system? 2, right? 2. So as a result, you will have 2 for your DOF. What does that mean? There are 3 unknowns in this system. What you need is 2 information among these 3. Then you can get the rest of it. You can get the rest of the one. For example, if I give you the pressure and temperature, this is the normal case. If I give you the temperature and pressure, you will get the molar fraction of the water in the gas phase. Okay? If I give you the molar fraction of the water in the gas phase and temperature, you can realize the pressure in this system. That's what the meaning of the DOF. Okay? Good. So only 2 out of 3 intensive variables, Tp and the molar fraction of water, can be specified. Some relationship must exist that unequally determine the value of the third variables once the first 2 have been specified. Right? So you must have an equation related to these 3. So if I tell you these 2, and you can get the third one. Right? So they must have an equation. And what is this equation? This is what we call Law's law. Law's law. So if I say, before we talk about Law's law, so once I give you temperature and pressure, you can get this. You can get molar fraction because of Law's law. And how about if I ask you the partial pressure of the water? water vapor? Can you get that? Dalton's law. So in this section, the things you want to know is only two laws, Law's law and the Dalton's law. This is Dalton's law. And we learned this in chapter 5. So Law's law first. So Law's law is a single condensable species for the single condensable species. Law's law is a law that describes the behavior of the gas-liquid systems over a wide range of conditions, provides the desired relationship. What kind of relationship? Temperature, pressure, and the molar fraction of the water vapor. Okay? So this is Law's law. So actually, what you need to remember is this. This is what we call Law's law. Yi times capital P equal to Xi times the Pi over star function of T. So what is P? P is the total pressure in the gas system. Yi is the molar fraction in gas phase for I species. Xi is the molar fraction of the Xi species in the liquid phase. And the Pi star function of T is what? The vapor pressure of the I species at the temperature T. So what can we get this? You can get this through Anton equation, right? You can get this through Koch's chart. That's why we just introduced you. You can get this through Clausius-Krypton equation. Okay, you can get this because you have single component T and relationship P and T. Okay, so this is what we call pure components vapor pressure at the system temperature T. Okay, so this is what you need to remember Law's law. However, in this section, what you can see is this equation. You might say, wow, Professor, this is different from this one. But actually, this is exactly the same. Why? Because Xi is equal to 1. Because this section we're talking about only one condensable components. And Xi is equal to 1. So if you put Xi here, and Xi is equal to 1, so you can get Yi times capital P equal to Pi star function of T, which is this one. Right? So this is what we call Law's law. And what is this? Dalton's law. Right? So you just do the combination of Law's law and the Dalton's law. That's it for this. Ladies and gentlemen, I want you to remember this very, very well. Because if you don't remember this, you also need to remember this when you study thermodynamics in the third grade. Okay? So how to obtain this one? If I give you T and P. So how to obtain the molar fraction of the water vapor if the pressure and the temperature are known? So this equation, right? So I give you the temperature and pressure in this system, and using the Law's law, you want to get Yi. This symbol is in red color. That means this is unknown. But if I give you temperature and pressure, first of all, you need to find out what? You need to find out vapor pressure of the water in the gas phase at what temperature, right? So according to the temperature, you need to find out vapor pressure of the water at temperature. Okay, so I hope you still remember I told you Clausius equation, Krypton equation, Anton equation, or Koch's chart, right? You get a vapor pressure. And then if you have a vapor pressure, you put this vapor pressure here. So according to total pressure and vapor pressure, you can get what? You can get molar fraction of the vapor pressure. Okay, so once you get the vapor pressure, and once you get the molar fraction, I want to ask you the partial pressure of the water. So partial pressure of water is what? If you have this and this, the partial pressure of the water is this. You can get the partial pressure of water vapor according to what? Dalton's equation. Okay? Easy. So let's do some practice. So example 6.3-1, composition of the saturated vapor, gas vapor systems. So if I give you a system, air and liquid water at 75 Celsius and 760 millimeter mercury. So I want you to calculate the molar composition of the gas phase. So here is, I give you 75 Celsius and 760 millimeter mercury in pressure, total pressure. And I tell you that this is air and water. And of course, there are only two species and only one condensable species, which is water. Okay, and we understand the molar fraction of the water in the gas liquid phase is 1. Okay, and now what we don't know is, according to this temperature and this pressure, what is the molar fraction of water? Well, you might ask me, what's the molar fraction of the air? We don't know, but you know these two are only one independent. Okay, these are not two independent variables, only one. Why? Because Y air plus Y water will be equal to 1, right? Okay, you only have two species. Okay, so let's think of how many species, how many information we need in order to create this system. So 2 plus C minus 1, how many species? 2, right? Okay, there are two species, air and water. And then how many phases? 2, right? So 2 information, bingo. If I give you the temperature and pressure, you can get molar fraction. So needs variables, temperature and pressure. So according to Law's law, I have P and T. Again, you need to get T. You have T, right? You need to know that vapor pressure of the water at 75 Celsius. What's the vapor pressure? Or we call partial pressure. Okay, so you check the table. Okay, and then once you know this, and you use the Law's law. Law's law tell you that P, you know the partial pressure of the water. You know the vapor pressure of water, saturated vapor pressure of water, and you can get this. So you move this around. P is here, right? 760 here, right? 760 here, and this one, what is this? This saturated vapor pressure is at 75 Celsius is 289 millimeter mercury. You can find out this in appendix, table B.3 in your textbook. Okay, I will help you to let's find this out together in the next page. Okay, so you know that this is 289 and this is 760. So, of course, you know the molar fraction of water vapor is 0.380. Obviously, the molar fraction of air is what? Is 0.62, right? Okay. So let's mark this in blue color because we will realize this. Okay. No problem. Okay. So if I want to ask you, what's the partial pressure of the water vapor in the gas phase? The partial pressure of water vapor is, you follow the Dalton's law again. So don't forget about this. So this is a bonus anyway. So once you create a system, I ask you one more information, you just use one more equation to solve the problem. Okay? Are you with me so far? Yes, right? Only 2 equations you need to remember. Law's law, Dalton's law. That's it. And you are dealing with molar fraction and pressure and temperature. That's it. So this is the table you can find out in your textbook. And as you can see, this is temperature. And related, so for example, this is 0, 0.0, 0.1, and this is minus 14, right? So what happened to this one? This is partial pressure, right? Partial, but we use the millimeter mercury as a unit. So this is what? Minus 14.0, minus 14.1, minus 14.2, okay? And this is, what is this? For example, this is 7, right? This is the ice, this is liquid. So 6.00, 6.1, 6.2, 6.3, and this is the partial pressure of the at a temperature 6.3, right? Okay, so in the example, in the exercise, that you need to find out the vapor pressure of the water vapor pressure at 75 Celsius. Where is 75? So this is 70. 25 to 49, 50, 60, 70, 80, right? So this is 70. And 70, 70, 71, 72, 73, 74, 75. So the vapor pressure is 289.1 millimeter mercury. Okay? Right. Apart from the to find out the vapor pressure using table, there are some charts, or there are some figures today. You can estimate the vapor pressure roughly. For example, this is the water, right? Water here. So you know the 75 here, and you go to the, this is about 10, 20, 30, 40. So 75 here, and you reach, you have a point close to 75 and this line, so you can get something like 30 something. Okay, millimeter mercury. K Pascal. Unit is different. Okay, so you have acetone, ethanol, water, and ethanolic acid, whatever. Right. So that next topic is related to two terms. The first term is called superheated vapor. The second term is called dew point. Dew point. Again, we are only talking about one condensable component. So what is saturated or saturation? I hope you already understand. Once the system reach equilibrium, and then the vaporization rate is equal to condensation rate, and the water is, you have two phases, and this system reach to equilibrium, and the vapor in the gas is saturated. That's why we call saturation. So at each time you have PI. Remember what is PI? Partial pressure, right? Partial pressure of water, for example. So in a gas in the equilibrium with a liquid must be saturated with the volatile components of the that liquid. We can use water, H2O, as an example in this case. Okay, reach equilibrium and saturated vapor. Okay, and we have PI. So once you have PI and PI star is saturated, right? So what's the relationship between PI and PI star? So if PI equal to PI star in a gas mixture, the vapor is saturated. Okay. For example, I hope you still remember I used the case of there's a container which is no water, and you start to pour water into this container. So the vapor pressure will increase in the very beginning. Okay, in the time equal to 1, time equal to 2, 3, 4, the vapor pressure will increase, which is PI. PI will increase until it reaches to equilibrium, and PI will equal to PI star. Okay, and this time vapor is saturated. So you might say, well, Professor, is it possible to make PI larger than PI star? Is it possible? No. You can. It's not possible. anything you want to make the Pi larger than Pi star, vapor will condense. So this is the Pi is the maximum. That's why we call saturated. Saturated. So you might say, wow, let's try. Let's try. So if this is Pi star, if I put more vapor into this system, what happens? Vapor will condense. Okay? So what happens if I increase the pressure in this system? What does that mean, increasing the pressure? Pressure means what? The number of the molecule, right? If I put more water vapor molecules in this system, what happens? You condense. So actually, there's no way to let Pi larger than the Pi star. No way. It is impossible. Okay? So this might be in your Kahoot next on Wednesday, right? Okay. Now I get your attention. Every time when I say Kahoot, I get all your attention. Everybody raise your head and see what's going on. I'm happy for this. Right, so behavior of the gas-liquid system, there's one term called superheated vapor. What does that mean, what does this mean, superheated vapor? So assume we have, let's go back to the condition that is the wet air. You have this, the temperature and the pressure is fixed, and water vapor is not saturated. So you have a tremendous water at this system. So this is initial stage. Time is equal to Ti. Okay, initial stage, I stand for initial. Okay, and this vapor pressure is Pi. And of course, you understand Pi was less than the Pi star. Why? Because it's not saturated. Okay, and the water vapor will keep on going up. So this Pi will increase until it reaches to equilibrium. So at time equal to EQU. EQ stands for equilibrium, right? So this is condition 1. You realize the amount of the water in liquid phase will reduce. Why? Because there are many water vapor come up from the liquid, and the water is saturated in the liquid in the gas phase. Okay, so this is what we call saturated. So at this time, we call Yi. So I hope you still remember at this point, Pi will equal to Pi star. Are you familiar with this equation? This is the combination of, this equation is the combination of Law's law and the Dalton's law, right? So you realize Pi will equal to Pi star, function of T. Okay? Right, and then, so what happens if you keep on increasing the temperature at this time? Because this is reached the saturation, right? And the water vapor increased and the liquid of water decreased. It reaches something like this. If you increase the temperature, then what happens? The water will going up. Well, water will vaporize again, one more, until what? And until there's no water. So temperature 2 must be larger than temperature 1, or the pressure 2 must be less than pressure 1, right? Okay, so, and what happened at this time? This time, Yi is huge, right? And then this is what we call super vapor. At this time, the vapor in the gas phase is called superheated vapor. So there's no liquid of H2O. Can you create this? Can you create this situation? Yes. Every time if you go to sauna, 三温暖, you go to that very hot room with a lot of woods. Remember, you get very, very hot. You sweat all the time. very, very hot, extremely hot, like you go to desert. There's no water. Water will be sucked out all the time. Okay, that's condition 1. And you go to condition 2 is you go to a steam room. Now, the water vapor is saturated. The water vapor is huge. We have steam room, right? Steam room. So you normally if you go to sauna, you will have these 2 rooms. And this is the one room which is like a desert. And water vapor is very, very hot. That's why we call it superheated vapor. Superheated. So once you have another drop of water come into this room, come into this environment, water will become vapor immediately and gain the energy. Water liquid gain the energy and then become water vapor. So you can make this temperature very, very hot. 400 Celsius, 500 Celsius, 600 Celsius. Well, I don't know if it's possible to reach 600 Celsius or not. I don't know any reaction will take place or not. But anyway, so this is condition 2. So condition 2 can move from the condition 1, or you can directly move to the condition 1 past this condition, move to this condition 2 without condition 1. Okay, I just want to let you understand there's a kind of situation which is the creation of the superheated vapor. So at this time, the Pi will always less than Pi star. Why? Because the Pi star will be, as I just told you, if you have a drop of liquid put into this chamber, the liquid will vaporize. Water will vaporize immediately. That means what? The Pi, you haven't reached the saturated vapor pressure yet, right? Otherwise, you will have water here, liquid water here. So Pi will less than the Pi star. So at this time, Pi will less than Pi star, but at this time, no water, Pi will always, again, will less than Pi star, but this reach to equilibrium. This is not. This is not. This is kind of dynamic, right? The vapor pressure increase and increase, but this reach the equilibrium. Okay? And this is what we call superheated vapor. So what is superheated vapor? So a vapor present in a gas is less than its saturated condition. So this Pi will be less than Pi star. Okay? It's referred to a superheated vapor. So Pi will equal to Pyi times P less than Pi star function of T. So Law's law still apply. Dalton's law still apply. Why? Because this is equilibrium. This is thermodynamics. It's nothing to do with the time. So superheated vapor, how do you make the superheated vapor become saturated vapor? How can you create saturated vapor with this condition? How? Decrease the temperature, right? Because temperature too high from here, and then if you increase the temperature, it becomes saturated. From saturated temperature, saturated vapor becomes superheated vapor, right? So once you decrease the temperature, the liquid will drop. The first drop of liquid will come out. So you have 2 strategies. The first strategy 1 is what? Decrease the temperature. So you got liquid come out. What's the second? Increase the pressure, right? If you increase the pressure, you push the pressure, and then water will come out. Okay, that's what we learned in section 6.2, right? 6.1, I'm sorry. Okay, strategy 1, decrease the temperature. Strategy 2 is increasing the pressure. So you can create saturated vapor from superheated vapor. Easy, right? Use water as an example. And you put the temperature and pressure around so you understand this situation. So decrease the system temperature to achieve condensation in a system condition containing a superheated vapor, or increase the total pressure. That's what I'm showing you here. Okay, so the second term is what we call dew point. What's the dew point? Once you start to decrease the temperature from this system, which is the superheated vapor, which has a superheated vapor. Once you start to decrease the temperature, the first drop of the water come out, and the temperature is what we call dew point. So if a gas containing a single superheated vapor is cooled at a constant pressure, the temperature at which the vapor becomes saturated is referred to as the dew point of the gas. So dew point, we call dew point temperature. You will learn two terms in the future, dew point temperature and dew point pressure. So once you playing temperature and pressure around, you decrease the temperature, you got dew point temperature. Okay? If you increase the pressure, you got a first point of the pressure, first drop of the water, you call dew point pressure. Okay, so from superheated vapor to saturated vapor, and the first drop is called dew point. So if you want to apply this to the Laws law, that will be T will be dew point. So you play temperature around from decrease the temperature from, for example, 100 Celsius to 90 Celsius to 80 Celsius, and 90 Celsius is dew point, for example. So differences between the temperature and the dew point temperature of the gas is called degree of the superheated gas. So you have, as I told you, that if you have superheated vapor, you can increase the temperature more and more. It's still superheated. So you need to know the degree of the superheated vapor and the dew point temperature. You need to know the superheated temperature and the dew point temperature. And the two differences between superheated temperature and the dew point temperature is what we call the degree of the superheated of the gas. We are going to have an example. Okay, so we will practice this. So the temperature at superheated situation minus the temperature at the dew point is called degree of superheated of the gas. Okay, so this is the example, 6.3-2. I give you the temperature, I give you the pressure, I also give you the molar fraction in the vapor phase. And I want you to calculate what if I decrease the temperature, and then what's the first drop of the water come out. And at that time, that's called dew point. And I also want you to find out the degree of the superheated of the air. Okay, so before we go through this example, let's have a break. Not really break. So this is the example. I give you a temperature and a pressure. I even give you the value, the fractional value in gas phase. Okay, so I want you to decide the dew point and the degree of the superheated of the air. So there's only one thing bother you, is this one, 10%. Why is 10% value fraction in gas phase? I really hope you remember when I talk about PV equal to nRT, we talk about the value fraction is equal to the molar fraction, because PV equal to nRT. So you want to know the value fraction, you need to know the molar fraction. And as long as I tell you the value fraction, that will be equal to the molar fraction. So actually, this is what we know is a molar fraction. Okay, so molar fraction in gas, I told you that. So molar fraction of the water is 10%, right? Molar fraction of water is 10%. So water is 0.1. So at this time, so I told you temperature and pressure and the molar fraction of water. So at this point, is any liquid water here or not? You don't know. So you need to find out what? You need to find out under this condition, is this vapor saturated or not? If this is saturated vapor or this is a superheated vapor. So how can you find out? How can you find out? Okay, let's do it. So this partial pressure of water is what? Okay, so partial pressure of water is what? Is according to Dalton's law, right? Dalton's law, 0.1 times capital P, total pressure. So the partial pressure is 526 millimeter mercury. Is this saturated? At this condition, 100 Celsius. So check the book, check the table, right? Check the table first. When the temperature reaches to 100 Celsius, what's the partial pressure of water at that time? Anybody tell me, what is the partial pressure of water? 1 atm, right? 1 atm, right? But then what happened? Then your pressure like 526. So it's less than 1 atm, which is 760 millimeter mercury. So is this vapor saturated? No. Pi is less than Pi star. And this reached to equilibrium. So is this condition, what we call this condition? Superheated vapor, right? Superheated vapor. Okay, so there's no water because the saturated water vapor is 760. So the Pi star is 100, if you check the table, is 760 millimeter mercury. This is common sense. I think you learned this in high school, right? That's what the boiling of the water, right? 100 Celsius, 1 atm, water start to boil. Okay, so you understand partial pressure of water is less than the saturated vapor pressure of the water. So so according to this equation, according to this condition, you realize this vapor is superheated. Okay? And what happened? So this is superheated vapor. And now I want you to find out the dew point. So what's the dew point? You decrease the temperature, right? If you decrease the temperature from 100 to 95, 90, 85, 80, and you find out there's the first drop of the water come out, and at that time, this is called dew point. So, for example, like 90 degree. So now you have 100 degree and 90 degree. The degree of superheated of the air is what? It's 10. Right? Because the first drop of the water come out is 90 Celsius, for example. So 100 minus 90 will become 10. So the degree is of the superheat of water is 10. Okay? I hope you understand what I'm talking. Anyway. Right, so if this equal to this 526 millimeter mercury, and then this is saturated. So you find out this vapor pressure. Okay, so you decrease the temperature, you will find out the pressure reach to equal, right? You need the vapor pressure equal to saturated vapor pressure, and we realize now the vapor pressure is 526. So you check the table. And if you have 526 millimeter mercury, what is the temperature of the water? And we realize the temperature of water is 90 Celsius. So the degree of superheated air of the air is 10 minus 90 equal to 10. So the key in this question is that you need to find out, first of all, you need to realize Dalton's law in order to know this is saturated or not. Key point 1. Key point 2 is you need to realize, use the table to find out the vapor pressure at the 526 millimeter mercury. What is the saturation temperature? Which is 90. Okay, this is the table. I give you the vapor pressure of the water, 526 millimeter mercury. How do you find out the temperature? So you find out 526. Where is 526? 526, 27, 25 is somewhere around here, right? 25 to 20, 25 to 20, 26, right? 26, 25.7, this is 27. So it's somewhere here. Well, we can say just 90, right? This is 90. Okay, you say, Loa, Professor, I'm not happy. It's 90.05. That's fine. It's up to you. Okay. Right. The question 2 is that calculate the percentage of the vapor that condensed and the final composition of the gas phase if the air is cooled to 80 Celsius at a constant pressure. So we have constant pressure, and then we drop the temperature from 100 Celsius to 90, right? 90 Celsius, the first drop of the water come out. And then once we continue to decrease the temperature to 80 Celsius, you will have more water, right? At that time, I want to ask you, what is the molar fraction of the vapor pressure? Molar fraction of the vapor, the water vapor. Or I can ask you the composition of the gas phase, right? So the point is that from 100 Celsius decrease to 90 Celsius decrease to 8. So you already know this dew point, right? And it decreased to 80 Celsius. So there are more and more water vapor condensed. So if you want to draw a flow chart, and if you think this is a continuous process, and in that case, you have a condenser. Okay? This condenser, the temperature is 80, and the temperature is the pressure is 5,260 millimeter mercury. Okay? And then, and you need to find out the vapor pressure of the water of the H2O at 80 Celsius is 355.1. Again, you check the table I showed you previously on the previous page, right? Okay, so you realize this is 355.1 millimeter mercury. So you write down here. So let's write down the mass balance in this case. So 100 mole basis, right? Well, we always use 100 mole, 100 as a unit. So we understand the water vapor is, molar fraction of water is 10%. And BDA is bone dry air. There's no water, so that's why I call bone dry air. The bone dry air is 90%. The temperature is 100, as we know. The pressure is 5,260 millimeter mercury. This is the initial condition, right? So we keep on feeding this to a condenser and want the liquid to come out. Okay, if we use as a kind of continuous process, and we need to have a gas phase. The gas phase, so water is N1. Water is N1. Okay, you want to know how many water come out per second or per hour, whatever. And then you realize you have N2, you don't know. And then what you know is that the temperature reached to 80 Celsius. So the molar fraction, you also don't know the molar fraction. So there are 3 unknowns here. And what you know is at this time, the temperature is 80 Celsius. And pressure is the 5,260 millimeter mercury. That's what you know. So you have 3 unknowns in this case. And then you need to find out these 3 unknowns according to mass balance. But don't forget you have specification to use, which is Law's law or Dalton's law, right? So saturated water, that means you use Law's law. So this is saturated, this is an equilibrium, thermodynamic. So you have Law's law. So you know the relationship between Y and the total pressure and what's saturated pressure of the water. You can check this from the table. So you will notice and you can get this. So this, and you can get this. Okay, so you get this, and then according to input equal to output, you have water mass balance, and you also have bone dry air mass balance in these two cases. In order to create two equations, so you can get an answer of N1 and N2. Okay, let me say this again. In order to get Y, you need to use Law's law, and you know the total pressure, you know the saturated pressure of the water at temperature 80, right? Check from the table. So you got Yi. So you get the answer of this one, and in order to get answer of N1 and N2, use mass balance, input equal to output. So you got N1 and N2. Okay. I don't want to waste your time, so please check this by yourself. Get the answer, okay? So you have DOF is 3 unknown, 3 equations. Water input equal to output, bone dry air input equal to output, and Law's law. You got the answer. And Law's law at the outlet, please write down this by yourself. Please practice this. Okay, percentage of condensation. So percentage of condensation is that it's the more the water condensed. Okay, so you can please, I think you understand how to solve this problem. So this is the second question. The third question is calculate the percentage condensation and the final gas phase composition if instead of reducing water from 100 to 90 to 80, we increase the pressure. So the air is compressed isothermally. Isothermal means what? You keep the temperature as a constant. So you increase the pressure from 5,260 to 8,500 millimeter mercury. So you increase the pressure. That means what? You press this. You have a piston. You push this piston down, and you squeeze this air and make it become water. To make water vapor become water. Right? Okay. So let's find out how to do this. So if you increase, you will come out with water, right? Because it increased the pressure from 5,000 to 8,000. Right. So let's find out what's the saturated pressure if you increase the pressure. So that means what is that? So from 5,000 you reach to 7,600, and the first drop of water will come out. That's one atm, right? That's for sure. Okay, you understand this? And then you keep on increase the pressure from 760 to 7,600 to 8,500. So you have more and more water condensed. And you need to calculate the amount of this water. Okay? So again, let's write down a flow chart, which is there as easier and as a kind of continuous process. You can play the temperature and the pressure around, and you can create this kind of situation. So you have 100 moles as a basis. Again, this is what we already know. 10% water, 90% bone dry air, and in the very input is 100 Celsius, 5,260 millimeter mercury pressure. Okay, only differences is the come out. So N1 is the same, N2, and then Y and 1 minus Y. This is the same, and the only difference is the final output condition. So again, we want to use Law's law in order to get Y, right? In order to get Y. So I don't want to waste your time. So this equation, so please do the practice this by yourself, okay? And you can find out the answer easily. Okay, so the question 4 is that suppose the process of the part 1. Let's skip this. You know, as an engineer, you always think that while the things I calculate theoretically is different from the data I receive, there might have some for example, like experimental errors, the condenser is not steady state. There are many situations which is unexpected. Situations are unexpected. So as an engineer, you will face the problem all the time, and you need to solve the problem. Okay. Right. So the end of this section is that why we need superheated vapor. This is one of very important topic, is that why we need superheated vapor. I told you superheated vapor has a tremendous energy. Why? Because there's no water. It's not saturated. So you can increase the temperature. So temperature means kinetic energy, right? If you increase the temperature tell you that the water vapor is very energetic. So this is what we use for the power station. Okay, you have, and how do you create electricity? By turbine, right? The turbine generator. Okay, so but how do you make the turbine move? You use superheated vapor to make the turbine move. How? You had to firstly create the superheated vapor. Now, how are you going to create superheated vapor? You burn the fuel to make the water become superheated vapor. Okay? So you use chemical energy. Again, you have chemical energy like coal or natural gas or fuels. Okay? You heat the water, and to make the liquid water become water vapor. And because the energy is too high, you change it from the chemical energy to thermal energy. This heat energy, right? From thermal energy to mechanic, which is kinetic energy. From kinetic energy to become electrical energy. And you got electricity at home or here, right? So where is the key? This is the key. Turbine is the key. The superheated vapor goes through this part and condense and then recycle. You might say, well, Professor, can I use not superheated vapor? You don't allow any water here because this is a very fine structure. You don't want vapor. You don't want water. You only want vapor, a very strong, very high energy vapor. So you can move this turbine, blend, move, so you can create electricity. Okay? Right. So this is a summary. I don't want to talk about this. We can talk about this on Wednesday. So then you review this. Okay. So right. So I think that's it for today. I think we run out of our time today. So I think I will just stop here. Okay. So I hope you enjoyed the lecture today, and I will see you on Wednesday.